what I wanted to show you all is that we had been doing the Pythagorean theorem a lot before this, which is just a squared plus b squared is equal to c squared. And then we started special right triangles, and most of us were like, what is this? Where did this come from? And now that we've seen special right triangles, what I want to do is just sort of unlock the secret behind them, just kind of reveal what's behind curtain number one. And curtain number one is our 45, 45, 90 triangle. And what's behind this is that if we look at this as the Pythagorean theorem, what we can have is a squared plus b squared is equal to c squared. And you're thinking to yourself, okay, Mr. Hissner, but that's okay, that's cool, but how does this have anything to do with our special right triangle? And as you remember, I said this is just some value for these sides, for our two sides here, right here, our two legs, will be, that value will be equal to, the hypotenuse will be equal to that value times the square root of 2. And you all are skeptical. How could this be? This is preposterous. There's no way. It's impossible, you say. Well, we know that this is a isosceles triangle, so these two sides are the same. So this is actually a squared plus a squared is equal to c squared. And I'm not going to bore you with the proof, but instead I'm just going to use numbers to show. So instead of our star value, I'm just going to say, hey, how about we let star equal, I don't know, 3. So 3 squared plus 3 squared is equal to c squared. And remember that this value, c squared, or c rather, is going to be some number times the square root of 2. That's what we want to get. So this is 9 plus 9 is equal to c squared. This is 18 is equal to c squared. And then we can square root both sides. And so this is the square root of 9 times 2, because 9 is a perfect square. These two cancel, so we're left with just c. It's 9 is a perfect square. The square root of 9 is 3. Oh, and look what we're left with. The square root of 2. And what do we find c to be? Oh, 3 times the square root of 2. And you're thinking to yourself, Mr. Hissner, I wanted to know, how did we get from C to one of the sides, from C to A? Well, you see, what we find is actually that A will, or C will be equal to A in such that C will be divided. A is going to be equal to C divided by the square root of 2. And I won't bore you with this proof, but it's true. And we know, so this is going to be C square root of 2 over 2. But anyway, I'm not going to bore you with that, but you can use the Pythagorean theorem to find these out. Yeah, fun stuff. Big reveal. I'm a pickle. No, I'm not a pickle. Big reveal is that we've been looking at this 30, 60, 90 triangle just like this, and I'm surprised that no one figured this out. That if this bottom section here is 1/2 is going to be half of this hypotenuse. So this side here is half c. That means that if we double it, if I just slide this over to the side, and I double this, then this entire, if I would double this segment, then the whole segment now in yellow will just be, what's 1/2 plus 1/2? 7, 11, 91. No, it's just 1. So 1/2 c plus 1/2 c is 1 whole c. And I know that 1 whole c is just going to be c. It's just going to be c. So we have our entire yellow line down there. It's the same. And that means that if these two sides are the same, that means that this side is going to be the same as well. Because this is a right angle, which makes this angle here in white a right angle, which makes this angle up here 30, which makes this suspicious character a equilateral triangle, equiangular triangle. And so our 30, 60, 90 triangles actually has just been half of, it's just been half of an equilateral triangle. Big reveal. I know. Hold on to them seats. And again, I'm not going to bore you with this sort of proof. However, it's nice to consider, it's nice to just remember that, let's say, for example, if you did want to try and do the Pythagorean theorem here, which I think is an excellent exercise, it would just look like 1/2 c, this whole thing squared, plus b squared is equal to c squared. And what did we know about this? I'm just going to erase these values here. What did we know? Well, we knew that there was one of these values was always messy. And it was this value here in blue. This was our star value times the square root of 3. This was our star value times 2. And this was just our star value, just our base value. And I'm just going to go through and prove that, hey, that's true. Let's say, for example, I'm given that C, our hypotenuse, is 10. Well, I know that this will be half of 10, right? Half of 10 is 5. I know division. And then I need to find this number here, B. So let's do it. We have 10 is C. It's equal to 5 squared plus B squared. Okay, B squared is equal to, or not equal to rather, is plus 25 is equal to 100 because that's 10 squared. So B squared is equal to 75. B squared is equal to, well, square root both sides. How about that? So this would be the square root of, oh, perfect squares in there. It's 25 times 3. Uh-oh. Square and square root cancel out. B is equal to the square root of 25 is 5. And what are we left with? Square root of 3. So here we go. Notice, that's that value. Just like I said, is that we have this base value, star. Well, that's 5. 10 would be 2 times star. And then this is just going to be 5 times square root of 3. So, if you find yourself really struggling to remember 3 different possible values, what you could do is use your old trusty dusty Pythagorean theorem.